Hello, I'm going to start my skip through neural networks by introducing some of the basic concepts and showing how various common types of networks can be put into categories. The field of connectionist architecture is a very wide and varied one, with many different types out there, although you'd never know it from some of the introduction guides I've seen. In this talk, I shall mention only three types: the multilayer perceptron, the Hopfield net, and the cell assembly, as they illustrate the basic concepts I want to talk about. In later talks, I shall try to cover as many of the other types as I can remember, but first things first, eh? All artificial neural networks contain a number of units that take in some sort of input signal and produce some sort of output. On diagrams, these units are represented by circles connected to other circles by lines, showing the paths that the signals can take. Each unit is based, very loosely, on a type of cell in the body called a neuron, which is the type of cell that in vast numbers makes up the human brain and nervous system. All human brain activity is carried out by countless interlinked networks of these types of cell. I tend to be a little sloppy when referring to the units in artificial neural networks. Sometimes I call them neurons and sometimes cells. I try to catch myself doing it, but don't be surprised if the occasional reference to neurons or cells slips through. Similarly, I should really distinguish between neural networks present inside the brain and the artificial neural networks that we simulate in computer software, but I generally don't do that. When most researchers refer to neural networks, they mean artificial ones that we have created. Generally speaking, artificial neural networks are simulated in computer software. It is possible to find neural networks coded into dedicated hardware, and as artificial intelligence pervades society more and more, hardware neural networks will become more common. However, most, if not all, of the networks you'll meet will be implemented in software. Of course, that's fine for this channel, where we simulate things in JavaScript anyway. Neurons are considerably more complicated than this diagram would suggest, but it's good enough to explain their basic function. The body of the cell is called the soma, and it receives electrochemical stimulus from other neurons through those branch connections called dendrites. The electrochemical stimulus builds up in the soma until it reaches some tipping point, at which point the neuron produces an output through the long connection called its axon. People often consider neurons to be akin to simple electrical devices, in which case you can think of the neuron as being charged up through its dendrites. When the cell's charge reaches a critical value, it discharges through the axon, passing its stored charge to other neurons whose dendrites are connected to that axon. The connections between the axon of one cell and the dendrites of others are termed synapses, and these connections have different strengths. A strong synaptic connection would pass the stimulus from one cell to the next efficiently, whereas a weak connection would largely block it. The processing that is carried out by networks of brain cells is determined by the pattern of connection strengths between the different cells, and the networks adapt their behavior by changing the strengths of the synaptic connections. Indeed, this is how we, as human beings, learn, by changing the strengths of the synapses in our brains. Now, if you type the phrase neural network or connectionist architecture into a search engine, the chances are you will soon come across a diagram like this one. This is the schematic layout of a very common type of neural network called a multi-layer perceptron. We have taken that description of neurons that you've just seen and boiled it down even further. But even so, these MLPs do still have a lot in common with real networks of neurons and function similarly. Like networks of cells in the brain, MLPs too consist of various units, the circles in the diagram, which receive input signals from some units and pass them on to others. The arrows in the diagram show that the signals travel from left to right. Just like any computer program, you need a way of getting data into the MLP, and it has to produce some sort of useful result. The network has inputs on the left, which is how you basically pump information into it from the outside world. Similarly, it produces a final output on the right. Signals pass along the connections, just like the synapses and networks of actual brain cells. We don't distinguish between dendrites and axons here. There is simply a connection between one cell and the next, and each connection has a certain strength, often called a weight. A connection with a large weight is an efficient one, and passes a large proportion of the output signal from one cell to the input to the next. A small weight blocks the signal by only passing on a small fraction of it. So what happens is that you present an input pattern to the units on the left, and the signal passes through the network, producing a corresponding pattern on the output. An MLP is a pattern associator. It learns to associate a series of input patterns with correct output patterns that correspond to them. Take SexNet, for example. SexNet was a multi-layer perceptron developed by a team led by Terry Sinofsky at the Salk Institute, designed to classify pictures of people into two categories, male and female. The inputs on the left are the pixels of the images, and there are two outputs on the right, one for male and one for female. The weights between units are adjusted so that images of men produce a high value on the male output and a low one on the female output, and vice versa for pictures of women. The MLP is probably the most common sort of artificial neural network because it is easy to implement and the mathematics underpinning it is widely understood. But there are other types, as I said. What you see on the screen is a diagram of a Hopfield net. It too consists of units with weighted connections, and it takes input from the outside world and produces a corresponding output. However, there is one important difference between a Hopfield net and an MLP. In the MLP, the connections only ever fed the signal one way through the network, from left to right, and so that sort of network is called feed-forward. In the Hopfield net, signals loop back on themselves. Of course, there still has to be inputs from the outside world, and the network still has to produce an output at some point. Otherwise, what will be the point of the thing? The Hopfield net only produces that output after the signal has looped back on itself several times through the network. This gives us the first way of categorizing neural nets. Networks like the MLP, in which the signal travels in one direction only, are feed-forward nets, while networks that contain signal loops, like the Hopfield net, are called recurrent networks. Another difference between these two architectures is that the patterns of outputs in the Hopfield net are the same as the input patterns. Effectively, a pattern of inputs is presented to the units and the connections are adjusted so that it produces the same pattern of outputs. This might sound a bit stupid. After all, what would be the point of presenting a pattern only to get the same pattern out? Well, it's not as silly as it sounds. The idea is that after the weights have been adjusted, you can present at the inputs variations of the standard patterns that net recognizes, maybe patterns that are incomplete or that have a great deal of corruption. The signals will go round and round the units in the net, we say the net iterates, and change gradually so that what comes out is a clean or uncorrupted version of one of the standard patterns. In this way, the Hopfield net can turn some unknown input into one of the standard patterns on which it has been trained. MPs aren't like that at all. Those nets are classifiers, which have a series of outputs representing different possible categories. In the case of SexNet, for example, there are only two outputs, representing male and female, and one of them is selected for any particular image at the inputs. This gives us another way of categorizing networks. MLPs are associative, meaning that they tie up input patterns with specific patterns of outputs. Hopfield nets are auto-associative, meaning that they associate patterns with themselves and can reconstruct a standard pattern from anything presented to the inputs. We have touched upon another aspect of neural networks obliquely here, and that's the fact that they need to be trained. We can't just throw together a large number of units and weighted connections and expect them to represent some sort of intelligent model of the world. The connections have to be adjusted so that the output produces a sensible one. In the case of MLPs, the training data comes in the form of input patterns, each of which is labelled with the correct category. If an MLP were intended to recognize spoken words, for instance, then it will be trained on a series of word patterns and told what each of those patterns should be. A Hopfield net also has a training data, but in this case, that just consists of a set of patterns. It doesn't need to know what those patterns represent. However, there is another kind of network that doesn't need similar training data. Such networks adjust their internal connections for themselves, according to rules that encourage them to produce similar outputs for input patterns that are similar, even though the identity of those patterns isn't known. For instance, a network that is designed to distinguish between pictures of cats and dogs will be presented with several of each, and would adjust its own connections so that it produced similar outputs for the cats and different outputs for the dogs. The dog outputs will be similar to each other, but different from the cat outputs, of course. Effectively, the networks will decide for themselves how to classify the input patterns without being told. One example of such a network is the cell assembly. This is a bit more closely modelled on the structures believed to be present in the human brain than other networks, such as the MLP or Hopfield net. It consists of a large number of units with connections initially set at random. Inputs are then presented to some of those units to represent patterns in the outside world, and the CA adjusts its internal connections according to certain rules. Patterns of activity develop across the units, and the rules are set so that similar patterns of activity will occur if similar inputs are presented. The outputs of the network are obtained simply by observing which units produce activity and which ones don't. In this way, cell assemblies build up their own patterns of internal activity which are unique for all the input patterns presented to them. These patterns are the CA's way of classifying those inputs. Now we have a third way of categorizing patterns, namely whether they are taught specific classifications, which the human controlling them has to decide in advance, or classify patterns for themselves, which makes them self-taught. There are other categories that we could put them in. For instance, Hopfield nets can only run on binary inputs which are 1 or 0, and produce binary outputs, whereas the other two types mentioned here can work equally well on binary inputs or continuous valued ones. Some neural networks, such as coherent nets, contain internal connections which are inhibitory, i.e. the output from some units can be used to shut down others. Perhaps we need a neural network whose job it is just to classify other neural networks. This talk was intended to do nothing more than touch upon some aspects of neural network architectures. I won't go into any further detail here, as the video is probably long enough already. However, in the next talk, I shall start tackling them in more detail, starting with the multi-layer perceptron. It is, after all, the sort of neural network that you are most likely to meet in the outside world. However, before that, there will, of course, be a JavaScript project. I haven't decided what that will be yet, but you'll find out